As you watch this video, your body is composed of roughly 7 octillion atoms. That's a 7 followed by 27 zeros. But here's what should disturb you about this fact. Each of those atoms is 99.9999999999996% empty space. The nucleus of every atom in your body occupies such a tiny fraction of the atom's volume that if you scaled an atom up to the size of a football stadium, the nucleus will be smaller than a marble sitting at the center of the field. Tonight, we're going to explore one of the most profound paradoxes in all of science: how nothingness creates everything we know as solid reality. We'll discover why atoms maintain their size despite being mostly empty, how electromagnetic forces create the illusion of solidity, and why quantum mechanics makes the very question, what is matter, far more complex than anyone imagined. You'll learn why you've never actually touched anything in your entire life, despite constantly feeling like you're touching solid objects. We'll explore how the same emptiness that makes up your body also creates the hardest substances known to science, and why some materials can pass through others while most cannot. Now let's begin our exploration of how emptiness becomes everything, starting with a journey into the vast spaces that exist within every atom in your body. Chapter 1. Atomic Scale to understand why matter feels solid despite being mostly empty space. You must first comprehend the almost incomprehensible scale of emptiness within atoms. The numbers involved are so extreme they challenge human ability to visualize them. Yet these measurements are among the most precisely known quantities in all of science. An atom consists of a tiny nucleus surrounded by electrons occupying regions called electron shells or orbitals. The nucleus contains protons and neutrons packed into a space roughly 100,000 times smaller than the overall size of the atom. To put this in perspective, if an atom were enlarged to the size of a football stadium, the nucleus would be about the size of a marble, sitting at the 50-yard line, and the electrons would be tiny specks orbiting somewhere in the upper reaches of the stadium. Dr. Brian Cox at the University of Manchester often uses an even more dramatic comparison. If you could enlarge a hydrogen atom so that its nucleus was the size of a ping-pong ball, the electron would be orbiting at a distance of about 2 kilometers away. The space between them would be completely empty. No particles, no structures, just void. But these comparisons, while helpful, actually underestimate the true emptiness of atoms. The nucleus occupies only about 1/4 of the atom's volume. That means 99.9999999999999% of every atom is empty space. In your body, which contains roughly 7 octillion atoms, the total volume of all the nuclei combined would be smaller than a grain of rice. Everything else about you, your height, width, the space you occupy in the world, is emptiness. The electrons that orbit these tiny nuclei don't fill the remaining space in any meaningful way. Unlike planets orbiting the sun, electrons don't have definite positions or paths. Instead, they exist in probability clouds that describe where they might be found if you could somehow observe them. Even when electrons are most likely to be found in certain regions around the nucleus, they're still point particles with no measurable size. Dr. Victor Stenger, former professor of physics at the University of Hawaii, calculated that if you could somehow squeeze all the empty space out of human atoms, a person weighing 70 kilograms would be compressed to a volume smaller than a grain of sand. All of humanity, every person who has ever lived, could be compressed to roughly the size of a sugar cube if you eliminated the empty space in their atoms. This emptiness isn't unique to simple atoms like hydrogen. Even the heaviest naturally occurring atoms, like uranium with 92 protons and up to 146 neutrons in their nuclei, maintain the same vast proportional emptiness. Adding more particles to the nucleus doesn't significantly change the overall size of the atom because the electron shells adjust to maintain roughly the same atomic radius. The scale of this emptiness becomes even more remarkable when you consider what fills the space between nucleus and electrons. It's not air, not some ethereal substance, not even the quantum foam that physicists theorize might exist at the smallest scales of space and time. It's quite literally nothing. No matter, no energy, no structures of any kind. Yet this nothingness has structure in the sense that it's organized by forces and principles that create boundaries and relationships. The empty space within atoms isn't chaotic or random. It's precisely organized by electromagnetic forces and quantum mechanical rules that determine exactly where electrons can exist and how they behave. Dr. Leonard Susskind at Stanford University describes atomic structure as organized emptiness, void that's structured by invisible rules to create the appearance and behavior of substantial matter. The forces that organize this emptiness operate according to principles that were completely unknown until the 20th century and still challenge our intuitive understanding of how reality works. The measurement techniques that reveal this atomic emptiness represent some of the most ingenious experiments in scientific history. Rutherford's gold foil experiment involved firing alpha particles, helium nuclei, at a thin sheet of gold atoms. Most particles pass straight through, confirming that atoms are mostly empty space. But about 1 in 8,000 particles bounced back, indicating they had hit something extremely small and dense, the atomic nucleus. Modern techniques have refined these measurements to extraordinary precision. Using X-ray crystallography, electron microscopy, and particle accelerator experiments, scientists can map atomic structure with accuracy measured in fractions of angstroms units so small that 10 billion angstroms equal 1 meter. Scanning tunneling microscopes can actually see individual atoms by measuring the quantum mechanical tunneling of electrons between a sharp probe and a surface. These images reveal atoms as fuzzy spheres of probability rather than solid objects, confirming that even our most direct observations of atoms show them as organized regions of emptiness rather than substantial particles. The emptiness of atoms also explains many properties of matter that would otherwise seem mysterious. Why can X-rays pass through your body while visible light cannot? Because X-rays have enough energy to pass through the empty spaces within and between atoms, while lower energy visible light interacts more readily with electron clouds. Your body is transparent to X-rays precisely because it's mostly empty space. Radioactive decay provides another window into atomic emptiness. When an unstable nucleus spontaneously emits particles, those particles must travel through the supposedly solid matter around them. Alpha particles, beta particles, and gamma rays can penetrate various materials because they read traveling through regions that are almost entirely empty space. The concept of atomic emptiness also helps explain why different materials have such different densities despite being made of the same basic components. Lead feels much heavier than aluminum, not because lead atoms are more solid, but because lead nuclei contain many more protons and neutrons packed into similar-sized atomic volumes. The emptiness remains the same. What changes is how much nuclear matter occupies the tiny central region. Even the hardest substances known to science, diamond, tungsten carbide, neutron star material, maintain this fundamental emptiness at the atomic level. Diamond's incredible hardness doesn't come from atoms being more solid, but from the particular way carbon atoms arrange their electron clouds to create extremely strong bonds across the mostly empty crystal structure. This raises a profound question. If atoms are organized emptiness rather than solid objects, what determines where one atom ends and another begins? The boundary between atoms isn't like the surface of a marble or planet. There is no definite edge where matter suddenly stops and empty space begins. Instead, atomic boundaries are fuzzy regions where electron probability clouds gradually fade away. Dr. Roald Hoffmann, Nobel laureate in chemistry, describes atomic boundaries as probabilistic surfaces rather than physical borders. Two atoms are separate, not because there's empty space between solid objects, but because their electron clouds create regions of electromagnetic influence that don't overlap significantly. The emptiness of atoms also connects to fundamental questions about the nature of space itself. If 99.99999999999% of matter is empty space, does that space have properties? Is it the same as the space between stars and galaxies, or does it have different characteristics because it exists within atomic structure? Quantum field theory suggests that even empty space is filled with quantum fluctuations, virtual particles that briefly pop into existence and disappear again. This means the emptiness within atoms might not be truly empty, but instead filled with quantum activity that we can't directly observe. Understanding the scale of atomic emptiness is essential for grasping why matter behaves as it does. The vast spaces within atoms aren't just interesting trivia. They read the reason matter can be compressed under extreme pressure, why some particles can pass through solid objects, and why the universe can contain such an enormous variety of substances despite being made from a relatively small number of basic building blocks. But recognizing the emptiness of atoms immediately leads to the central paradox. If individual atoms are almost entirely empty space, why don't collections of atoms simply collapse into nothing? The answer lies in forces and principles that operate within that emptiness to create barriers more substantial than any physical wall. Chapter 2. Nuclear forces. At the heart of every atom lies a nucleus so incredibly dense that a single teaspoon of nuclear material would weigh about 5 billion tons. This tiny region, occupying less than 1/4illionth of the atom's volume, contains virtually all of the atom's mass packed into a space smaller than you could see with the most powerful optical microscope. Understanding what holds this nucleus together and what keeps it from exploding apart or collapsing into nothing reveals the first key to why matter maintains its structure despite being mostly empty space. The nucleus faces a fundamental problem that shouldn't have a solution. Protons, which make up roughly half of nuclear particles, all carry positive electrical charge. According to electromagnetic theory, particles with the same charge should repel each other with tremendous force. The electromagnetic repulsion between protons in a nucleus is so powerful that it should instantly blow the nucleus apart, like trying to force dozens of powerful magnets together with their repelling poles facing each other. Dr. Frank Wilczek at MIT calculated that the electromagnetic repulsion between protons in a carbon nucleus generates a force equivalent to about 20 tons pushing outward on each proton. For heavier nuclei like uranium, this force becomes even more extreme. Yet somehow, atomic nuclei remain stable for periods ranging from microseconds to billions of years, depending on their composition. The force responsible for nuclear stability is called a strong nuclear force, and it operates according to principles completely unlike anything in everyday experience. This force is roughly 100 times stronger than electromagnetic repulsion, but it only works across distances measured in femtometers, units so small that a proton's diameter is just 1 femtometer across. The strong force has a peculiar characteristic that makes nuclear physics utterly unlike familiar mechanical systems. It gets stronger when you try to pull nuclear particles apart, rather than weaker like gravity or magnetism. Dr. David Gross, Nobel laureate at UC Santa Barbara, describes this as asymptotic freedom. Nuclear particles become more tightly bound the farther apart you try to force them. This creates a nuclear structure that's simultaneously incredibly stable and incredibly fragile. Within the tiny range where the strong force operates, nuclear particles are bound together more tightly than any chemical bonds. But if you could somehow stretch nuclear particles just slightly beyond this range, the strong force would vanish completely and electromagnetic repulsion would take over. The balance between strong force attraction and electromagnetic repulsion determines not only nuclear stability but also the fundamental structure of matter throughout the universe. Elements lighter than iron are held together by strong force binding that exceeds electromagnetic repulsion. Elements heavier than iron exist in a more precarious balance where adding more protons makes nuclei increasingly unstable. Neutrons play a crucial role in nuclear stability by providing strong force attraction without electromagnetic repulsion. In lighter elements, the ratio of neutrons to protons is roughly 1:1. But heavier elements require increasingly more neutrons than protons to maintain stability, because the strong force needs extra binding power to overcome electromagnetic repulsion from larger numbers of protons. This neutron-to-proton ratio explains why elements beyond uranium don't occur naturally on Earth. Super-heavy elements created in particle accelerators have so many protons that no amount of neutrons can provide enough strong force binding to overcome electromagnetic repulsion permanently. These artificial elements decay within seconds or minutes, returning to more stable configurations. The energy locked within nuclear binding represents the most concentrated form of energy storage in normal matter. Einstein's famous equation E equals mc describes how nuclear binding converts tiny amounts of mass into enormous amounts of energy. The mass of a complete nucleus is always slightly less than the mass of its individual components because some mass has been converted into binding energy that holds the nucleus together. Dr. Hans Bethe calculated that nuclear binding energies are typically 8 to 9 million electron volts per nuclear particle, roughly 1,000,000 times stronger than chemical bond energies. This explains why nuclear reactions release so much more energy than chemical reactions, and why nuclear fuel is millions of times more energy dense than chemical fuels like oil or coal. Nuclear forces also operate through quantum mechanical principles that make them fundamentally different from forces in everyday experience. Nuclear particles exist in discrete energy states, meaning they can only have certain specific binding energies. When nuclei transition between these states, they emit gamma rays, electromagnetic radiation so energetic it can penetrate thick layers of material that would stop visible light or even X-rays. The quantum nature of nuclear forces creates what physicists call magic numbers, specific numbers of protons or neutrons that create extra nuclear stability. Nuclei with 2, 8, 28, 50, 82, or 126 protons or neutrons are significantly more stable than surrounding elements. These magic numbers reflect the quantum mechanical shell structure within nuclei, similar to, but much more complex than electron shells around atoms. Understanding nuclear forces helps explain why atoms maintain their emptiness despite containing such powerful attractive forces. The strong force operates only within nuclear dimensions, leaving the vast empty spaces of atomic electron shells completely unaffected. Nuclear stability provides the foundation for atomic structure, but it doesn't eliminate atomic emptiness. It ensures that the tiny nucleus at each atom's center remains intact while electrons orbit through mostly empty space. Nuclear physics also reveals why matter can't simply collapse under gravity or other compressing forces. Even when atoms are pushed together under extreme pressure, their nuclei remain separated by the electromagnetic forces between electron clouds. The nuclei themselves cannot be compressed because nuclear particles are already bound as tightly as quantum mechanics and the strong force allow. Only under the most extreme conditions, inside neutron stars where gravitational pressure exceeds nuclear binding forces, do normal atomic nuclei get crushed together. In these environments, protons and electrons are forced together to form neutrons, creating matter so dense that a teaspoon would weigh as much as Mount Everest. The study of nuclear forces has practical implications that extend far beyond theoretical physics. Nuclear medicine uses radioactive decay to create medical isotopes that can target specific organs or tumors. Nuclear power plants harness nuclear binding energy by splitting heavy nuclei like uranium or fusing light nuclei like hydrogen. These technologies work because we understand how nuclear forces operate within the tiny spaces at atomic centers. Nuclear forces also explain why alchemy, the ancient dream of transforming one element into another, is theoretically possible but practically difficult. Changing one element into another requires altering the number of protons in atomic nuclei, which means overcoming or manipulating the strong nuclear force. While nuclear reactions can accomplish this transformation, they require enormous energies and sophisticated equipment. The discovery of nuclear forces in the early 20th century revolutionized understanding of stellar physics and cosmic evolution. Stars shine by converting nuclear binding energy into light and heat through fusion reactions that combine light nuclei into heavier ones. The carbon, oxygen, and other elements essential for life were created in stellar cores through nuclear processes that overcome electromagnetic repulsion to build increasingly heavy nuclei. Dr. Carl Sagan's famous observation that we are made of star stuff reflects the nuclear physics that created heavy elements in stellar furnaces. Every atom in your body heavier than hydrogen was forged in nuclear reactions that balance strong force attraction against electromagnetic repulsion under conditions of extreme temperature and pressure. Nuclear forces operate through quantum field theory principles that describe them as exchanges of force-carrying particles called gluons. These gluons mediate the strong force between quarks, the fundamental particles that make up protons and neutrons. The mathematics of gluon exchange explains both the incredible strength of nuclear binding and its extremely short range. Recent research in quantum chromodynamics has revealed that nuclear forces are themselves manifestations of an even more fundamental force operating between quarks inside nuclear particles. This deeper understanding shows that nuclear stability emerges from quantum field interactions that create bound states of quarks, which then interact through residual strong forces to create nuclear binding. Understanding nuclear forces provides the foundation for grasping how matter maintains its structure despite being mostly empty space. The nucleus serves as an incredibly dense, stable anchor around which electrons can orbit through vast empty regions. Nuclear binding energy ensures this anchor remains intact under normal conditions, providing the framework for atomic structure and ultimately for the solid matter we experience. But nuclear forces only explain stability within the tiny nuclear realm. The question remains: what prevents atoms from simply colliding with each other and collapsing the empty space between them? The answer involves forces operating in the much larger realm of electron shells, where different principles create barriers that feel like solidity. Chapter 3. Electromagnetic repulsion. When you press your hand against a wall, you feel solid resistance that prevents you from pushing through. Your brain interprets this sensation as contact between solid objects, but the reality is far stranger. Your hand never actually touches the wall. Instead, electromagnetic forces between the electrons in your hand and the electrons in the wall create a repulsive barrier that feels like physical contact but operates through invisible fields across empty space. This electromagnetic repulsion is the primary reason why matter feels solid despite being mostly empty space. It's not that atoms are packed together like marbles in a jar, but rather that negatively charged electron clouds around. Atomic nuclei repel each other when they come close together, creating what physicists call the contact force that dominates every tactile experience you've ever had. Dr. Richard Feynman explained this phenomenon with characteristic clarity. When you sit in a chair, you're not actually touching the chair. The electrons in your body are pushing against the electrons in the chair, and you feel this repulsion as the sensation of sitting on something solid. It's all electromagnetic forces. There's no actual contact between particles. The strength of electromagnetic repulsion follows Coulomb's law, which states that the force between charged particles increases dramatically as they get closer together. When electron clouds around different atoms begin to overlap, they experience repulsive forces that grow exponentially stronger the more you try to compress them. This creates an electromagnetic wall that becomes nearly impossible to penetrate under normal conditions. To understand the scale of electromagnetic forces involved in everyday contact, consider what happens when you push on a table. The electrons in your fingertips approach the electrons in the table-less surface material until electromagnetic repulsion becomes strong enough to halt further compression. This equilibrium occurs when electromagnetic forces exactly balance the pressure you're applying, creating the sensation of touching a solid surface. Dr. Walter Lewin at MIT calculated that electromagnetic forces in typical contact situations involve field strengths of thousands of volts per centimeter, even though the actual separation between electron clouds remains at atomic scales measured in angstroms. The electric fields involved in simple acts like picking up a pencil are comparable to those found inside high-voltage electrical equipment. But electromagnetic repulsion doesn't just create the sensation of solid contact. It determines fundamental properties of matter, including hardness, elasticity, and structural stability. Diamond's exceptional hardness results from carbon atoms arranged so their electron clouds create particularly strong electromagnetic repulsion when compressed. The covalent bonds between carbon atoms in diamond structure concentrate electromagnetic forces in ways that resist deformation more effectively than other arrangements. Conversely, materials like rubber or foam feel soft because their atomic structure allows electromagnetic repulsion to be distributed and redirected rather than concentrated. When you compress a sponge, you're not overcoming electromagnetic repulsion between atoms, but rather redirecting it as the material's internal structure rearranges to accommodate applied pressure. The electromagnetic origin of contact forces explains why some materials can pass through others while most cannot. X-rays penetrate your body because they have enough energy to interact differently with electron clouds than visible light or physical objects. Alpha particles from radioactive decay can penetrate materials because they moving fast enough that electromagnetic repulsion can't stop them before they pass through the mostly empty atomic structure. Temperature affects electromagnetic repulsion in ways that explain why matter expands when heated and contracts when cooled. Higher temperatures make atoms vibrate more energetically, which effectively increases the average distance between electron clouds. Lower temperatures reduce atomic vibration, allowing electromagnetic forces to pull atoms closer together before repulsion becomes dominant. Dr. Philip Anderson at Princeton University demonstrated that electromagnetic repulsion between electron clouds is responsible for virtually all mechanical properties of normal matter. Strength, flexibility, brittleness, and elasticity all emerge from how atomic arrangements channel and distribute electromagnetic forces when materials are stressed, compressed, or deformed. The quantum mechanical nature of electromagnetic repulsion adds layers of complexity beyond classical physics predictions. Electrons do not orbit nuclei in defined paths like planets around stars. They exist in probability clouds that describe where they might be found. When these probability clouds overlap between different atoms, quantum mechanics creates additional repulsive effects called exchange forces that enhance electromagnetic repulsion. Exchange forces arise from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. When electron clouds from different atoms begin to overlap, some electrons would be forced into identical quantum states if the atoms could get closer. Quantum mechanics prevents this by creating additional repulsive forces that maintain electron separation. Dr. John Slater at Harvard University showed that exchange forces can be even stronger than classical electromagnetic repulsion in determining contact between atoms. These quantum mechanical effects make matter more incompressible than purely electromagnetic calculations would predict, explaining why even the softest materials require finite force to compress and why all matter maintains definite volumes under normal conditions. The speed at which electromagnetic repulsion operates helps explain why contact feels instantaneous. Electromagnetic forces propagate at the speed of light, so when you touch something, the electron clouds adjust their repulsion patterns within nanoseconds. Your nervous system, which operates much more slowly through chemical and electrical signals, interprets this near instantaneous electromagnetic response as immediate contact. Electromagnetic repulsion also explains why friction exists between surfaces. When two materials slide against each other, their electron clouds interact through electromagnetic forces that oppose motion. The strength of these interactions depends on surface roughness, material properties, and the specific ways electron clouds can interact at the molecular level. Modern technology exploits electromagnetic repulsion in numerous applications. Magnetic levitation trains use electromagnetic forces to suspend vehicles above tracks without physical contact, demonstrating that electromagnetic repulsion can support enormous weights when properly configured. Touch screens detect finger position by measuring changes in electromagnetic fields without requiring actual contact between finger and screen. The electromagnetic basis of contact forces has philosophical implications for how we understand physical reality. Every sensation of touching, holding, or manipulating objects is actually electromagnetic interaction between electron clouds separated by empty space. You've never actually touched anything in your life. You've only experienced electromagnetic field interactions that your brain interprets as contact. This reality becomes even more remarkable when you consider that electromagnetic repulsion creates not just the sensation of contact, but also determines the shapes and sizes of all familiar objects. The chair you're sitting in maintains its shape because electromagnetic forces between its constituent atoms create stable equilibrium configurations that resist deformation. Dr. Steven Weinberg at the University of Texas describes ordinary matter as electromagnetic sculptures, three-dimensional arrangements of electromagnetic fields that create the appearance of solid objects through force patterns rather than actual substance. What we experience as the solid world is really an intricate tapestry of electromagnetic interactions operating across mostly empty space. The study of electromagnetic repulsion under extreme conditions reveals limits to how incompressible matter can be. Under pressures found deep inside planets or stars, electromagnetic repulsion eventually becomes insufficient to maintain normal atomic structure. Electrons get pressed so close to nuclei that they combine with protons to form neutrons, creating matter states where electromagnetic repulsion no longer determines material properties. Understanding electromagnetic repulsion helps explain why the scale of everyday objects falls within such a narrow range compared to atomic or cosmic scales. The strength of electromagnetic forces, combined with quantum mechanical constraints, determines that stable matter structures naturally form at scales ranging from nanometers to kilometers. Smaller structures lack sufficient electromagnetic binding, while larger structures exceed the strength of electromagnetic forces to maintain coherence. Electromagnetic repulsion between electron clouds is ultimately what prevents the empty space within atoms from collapsing. Without these repulsive forces, the vast atomic emptiness we've explored would indeed collapse, and matter would compress into incredibly dense nuclear material. Electromagnetic repulsion maintains atomic structure by creating force barriers that preserve the mostly empty architecture of atoms while making that emptiness feel completely solid to our senses. But electromagnetic repulsion alone doesn't fully explain why matter maintains specific shapes, sizes, and properties. The answer requires understanding quantum mechanics and how the wave-like nature of electrons creates additional constraints that determine the precise structure of atoms and molecules. Chapter 4. Electron clouds. The electrons that orbit atomic nuclei don't behave like tiny planets following predictable paths around a central star. Instead, they exist as probability clouds, wave-like distributions that describe where an electron might be found if you could somehow observe it. These electron clouds are responsible for virtually everything you experience as the solid properties of matter. Yet they themselves aren't solid objects, but rather mathematical descriptions of quantum mechanical probability. To understand how something that isn't even a definite object can create solidity, you must abandon classical thinking about particles and embrace the strange world of quantum mechanics. An electron cloud represents all the possible locations where an electron could exist around a nucleus, with denser regions of the cloud indicating higher probability of finding the electron in that area. The cloud never has sharp edges. It simply fades gradually into regions where the probability approaches zero. Dr. Linus Pauling, who revolutionized the understanding of chemical bonding, described electron clouds as standing waves that surround atomic nuclei. These waves can only exist in specific patterns determined by quantum mechanical rules, much like how a guitar string can only vibrate in certain harmonious patterns. The allowed wave patterns determine the size, shape, and energy of electron orbitals that define atomic structure. The mathematical description of electron clouds involves wave functions, equations that describe the probability of finding electrons at any given location around a nucleus. These wave functions have specific shapes designated by letters. S orbitals are spherical, p orbitals are dumbbell-shaped, d orbitals have more complex geometries, and f orbitals are even more elaborate. Each shape represents a different pattern of electron probability that contributes to atomic behavior. But here's what makes electron clouds truly remarkable. They are not just mathematical abstractions, but physical realities that determine how atoms interact with each other and with electromagnetic radiation. When atoms bond to form molecules, their electron clouds overlap and merge in specific ways that create new probability distributions, spanning multiple nuclei. Dr. Walter Kohn, Nobel laureate for his work on density functional theory, showed that electron clouds determine virtually every property of matter we can observe or measure. The hardness of diamond, the conductivity of copper, the transparency of glass, and the flexibility of rubber all emerge from specific patterns of electron cloud distribution and interaction. The size of electron clouds determines atomic size, which in turn determines how close atoms can approach each other before electromagnetic repulsion becomes dominant. Hydrogen atoms with their single electron clouds are the smallest atoms. Larger atoms have multiple electron shells, layers of electron clouds at different distances from the nucleus, that create larger overall atomic sizes despite containing the same fundamental emptiness. The Pauli exclusion principle plays a crucial role in determining electron cloud structure. This principle states that no two electrons can occupy the same quantum state, which forces electrons into layered shells around nuclei. Each shell can hold only a specific number of electrons. The first shell holds 2, the second holds 8, the third holds 18, and so on. This shell structure explains the periodic table's organization and why different elements have such different properties. While electron clouds from different atoms overlap, quantum mechanics creates bonding patterns that hold molecules together. In covalent bonds, electron clouds merge to create shared regions of electron probability that span multiple nuclei. These shared electron clouds act like electromagnetic glue, binding atoms into stable molecular structures that maintain their integrity across the mostly empty atomic space. Dr. Roald Hoffmann, Nobel laureate in chemistry, describes molecular bonding as electron cloud sculpting, the process by which overlapping atomic orbitals create new molecular orbitals. with shapes and properties that determine molecular behavior. Water molecules, proteins, DNA, and every chemical compound you can name exist because electron clouds combine in specific patterns that create stable structures. The wave-like nature of electron clouds also explains why atoms have definite sizes despite being mostly empty space. Electron waves can only exist in certain stable patterns around nuclei, and these patterns naturally extend to specific distances from the nuclear center. An atom's size is determined not by solid boundaries, but by the distance at which electron probability clouds fade to negligible levels. This quantum mechanical size determination explains why atoms resist compression under normal conditions. When you try to squeeze atoms together, you're attempting to force electron clouds into overlapping configurations that would violate quantum mechanical rules. The resistance you feel isn't from solid objects pushing back, but from quantum mechanical constraints that prevent certain electron configurations from existing. Electron clouds also determine how atoms interact with electromagnetic radiation. When light hits an atom, it interacts with electron clouds in ways that depend on both the light's frequency and the specific patterns of electron probability around the nucleus. Some frequencies can excite electrons to higher energy states, others pass through without interaction, and still others get absorbed or reflected based on electron cloud characteristics. The color of every object you see results from how electron clouds in that material's atoms interact with different frequencies of visible light. Red objects absorb blue and green light while reflecting red light because their electron cloud patterns interact more strongly with higher frequency blue and green photons than with lower frequency red photons. Dr. Ahmed Zeewell, Nobel laureate for his work on femtosecond chemistry, used ultrafast laser pulses to observe how electron clouds change during chemical reactions. His research revealed that chemical bonding involves rapid reorganization of electron probability patterns as atoms approach each other and their electron clouds begin to overlap and merge. The dynamic nature of electron clouds helps explain why matter can exist in different phases: solid, liquid, gas, and plasma. In solids, electron clouds are organized in rigid patterns that maintain fixed relationships between atomic positions. In liquids, electron clouds maintain bonding but allow more flexible atomic arrangements. In gases, electron clouds interact only briefly during atomic collisions. In plasmas, high temperatures strip electrons completely away from nuclei. Temperature affects electron clouds by changing their vibrational patterns and average positions. Higher temperatures make electron clouds more diffuse and energetic, which weakens the electromagnetic forces that hold matter together. This explains why materials expand when heated, and why all materials eventually vaporize if heated sufficiently. The quantum mechanical tunneling effect allows electron clouds to occasionally exist in regions where classical physics says they shouldn't be able to penetrate. This quantum tunneling enables chemical reactions that would be impossible under purely classical electromagnetic interactions and explains why some materials can conduct electricity even when their electron clouds seem to create insulating barriers. Modern scanning tunneling microscopes exploit quantum tunneling of electron clouds to create images of individual atoms. By measuring tiny currents that flow when electron clouds tunnel between a sharp probe and the surface, these instruments can map electron cloud density with atomic scale precision. Electron clouds also explain why chemical elements have such different properties, despite being made from the same basic components of protons, neutrons, and electrons. Carbon and silicon have similar electron cloud configurations in their outer shells, which explains why they can form similar types of chemical bonds. But subtle differences in their electron cloud sizes and energies make carbon ideal for biological molecules, while silicon is better suited for electronic applications. The magnetic properties of materials also emerge from electron cloud behavior. Electrons have intrinsic magnetic moments called spin, And the way electron clouds organize around nuclei determines whether materials become magnetic, remain non-magnetic, or actively oppose magnetic fields. Understanding electron clouds reveals that the solid world around you is actually a manifestation of quantum mechanical wave patterns existing in mostly empty space. Every object you can touch or see is really a collection of electron probability distributions that create stable patterns of electromagnetic interaction. The chair you're sitting in, the screen you're watching, and your own body are all quantum mechanical sculptures made from electron waves. But electron clouds alone still don't fully explain why matter feels solid, rather than just being collections of interacting probability waves. The final piece of this puzzle involves quantum mechanical principles that create absolute barriers, preventing certain configurations of matter from existing, regardless of how much force you apply. Chapter 5. Quantum Mechanics. Quantum mechanics doesn't just describe how atoms behave. It creates the fundamental rules that make matter possible. Without quantum mechanical principles, the electron clouds we've explored would collapse into atomic nuclei within a fraction of a second. All matter would instantly compress into infinitesimally dense points, and the universe as we know it simply could not exist. Understanding these quantum rules reveals why emptiness can feel solid, and why matter maintains its structure despite being almost entirely nothing. The most important quantum principle for understanding matter's solidity is the Heisenberg uncertainty principle, which states that you cannot simultaneously know both the exact position and exact momentum of any particle. This isn't just a limitation of measurement technology. It's a fundamental property of reality itself. Particles literally cannot have both definite positions and definite velocities at the same time. Dr. Werner Heisenberg discovered that this uncertainty principle explains why electrons don't spiral into atomic nuclei, even though electromagnetic attraction should pull them inward. If an electron were to fall into the nucleus, its position would become very precisely defined, which means its momentum would become very uncertain. Quantum mechanics requires that this uncertainty in momentum would make the electron's kinetic energy enormous, so enormous that it would immediately escape the nucleus. This creates what physicists call quantum pressure, a resistance to compression that emerges directly from quantum mechanical uncertainty. The more you try to confine an electron to a smaller space, the more uncertain its momentum becomes, and the more energy it requires to stay in that space. This quantum pressure provides a fundamental limit on how much matter can be compressed under normal conditions. Dr. Freeman Dyson at the Institute for Advanced Study calculated that quantum pressure is responsible for the stability of all normal matter. Without the Heisenberg uncertainty principle, atoms would collapse to nuclear density within Y-23 seconds. And chemistry, biology, and everything we know as material existence would be impossible. The Pauli exclusion principle provides another quantum mechanical barrier that prevents matter from collapsing. Wolfgang Pauli discovered that no two fermions, particles like electrons, protons, and neutrons, can occupy the same quantum state simultaneously. This principle forces electrons into layered shells around nuclei and prevents nuclear particles from occupying the same space, even when compressed by enormous forces. When electrons in neighboring atoms try to occupy overlapping regions, the Pauli exclusion principle creates additional repulsive forces called exchange forces that supplement electromagnetic repulsion. Dr. Paul Dirac showed that these exchange forces can be even stronger than electromagnetic repulsion in determining how close atoms can approach each other. The quantum mechanical description of electron behavior involves wave-particle duality, the idea that electrons exhibit both wave-like and particle-like properties depending on how you observe them. When electrons behave as waves, they create standing wave patterns around nuclei that can only exist in specific stable configurations. These allowed configurations determine atomic structure and explain why atoms have definite sizes despite being mostly empty. Space. Dr. Louis de Broglie discovered that all particles, including electrons, have associated wavelengths that depend on their momentum. The wavelength of electrons in atoms is comparable to atomic dimensions, which means quantum wave effects are crucial for determining atomic structure. These matter waves create interference patterns that allow only certain electron orbits to exist stably around nuclei. The quantization of energy levels in atoms emerges directly from wave-like electron behavior. Just as guitar strings can only vibrate in certain harmonious patterns, electron waves around nuclei can only exist in specific energy states. This quantization explains why atoms absorb and emit light at characteristic frequencies, and why chemical bonding follows precise rules based on electron energy levels. Quantum tunneling represents one of the most counterintuitive quantum mechanical effects that influences matter's behavior. This phenomenon allows particles to pass through energy barriers that classical physics says should be impenetrable. Quantum tunneling enables nuclear fusion in stars, radioactive decay, and many chemical reactions that would otherwise be impossible. In the context of matter's solidity, quantum tunneling explains why electromagnetic barriers between atoms aren't absolutely impenetrable. Under extreme conditions, particles can tunnel through these barriers, allowing matter to be compressed beyond what classical electromagnetic repulsion would permit. However, tunneling probabilities decrease exponentially with barrier strength, so normal electromagnetic repulsion remains an effective barrier under everyday conditions. Dr. Max Born developed the probability interpretation of quantum mechanics that explains how quantum mechanical wave functions relate to observable reality. According to Born's interpretation, quantum mechanical calculations don't predict exactly what will happen, but rather the probabilities of different outcomes. This probabilistic nature is fundamental to quantum mechanics and can't be eliminated by better measurements or theories. The probabilistic nature of quantum mechanics has profound implications for understanding matter structure. Electron positions around nuclei aren't precisely determined but exist as probability distributions that describe where electrons might be found. These probability distributions create the electron clouds we've discussed, and their shapes and sizes determine how atoms interact with each other and with electromagnetic radiation. Quantum entanglement creates correlations between particles that transcend classical physics and can influence matter's properties in surprising ways. When electrons become entangled, measurements on one electron instantly affect the quantum state of its entangled partner, regardless of the distance separating them. These quantum correlations play roles in determining the magnetic and electrical properties of materials. The quantum measurement problem raises deep questions about the nature of reality and observation. Before measurement, quantum systems exist in superpositions of multiple possible states. The act of measurement appears to collapse these superpositions into definite outcomes, but the mechanism of this collapse remains one of the most profound unsolved problems in physics. Dr. Hugh Everett, 3, proposed the many worlds interpretation as a solution to the measurement problem, suggesting that all possible outcomes of quantum measurements actually occur, but in separate parallel universes. While this interpretation remains controversial, it highlights how quantum mechanics challenges our basic assumptions about the nature of reality. Quantum field theory extends quantum mechanics to describe how particles and forces emerge from underlying quantum fields that fill all of space. According to quantum field theory, what we perceive as empty space is actually filled with quantum fields whose fluctuations create virtual particles that briefly appear and disappear. These quantum fluctuations may contribute to the properties of matter even in regions we consider empty. The study of quantum decoherence explains why quantum mechanical effects like superposition and entanglement typically do and persist in macroscopic objects. Interactions with the environment cause quantum superpositions to rapidly decay into classical-like states, explaining why everyday objects appear to have definite positions and properties rather than existing in quantum superpositions. Modern quantum technologies exploit quantum mechanical principles to create new forms of matter and new capabilities for manipulating material properties. Quantum dots confine electrons to regions so small that quantum effects dominate their behavior, creating materials with tunable optical and electronic properties. Bose-Einstein condensates represent states of matter where quantum effects become macroscopically observable. The role of quantum mechanics in determining matter's properties extends beyond individual atoms to influence how collections of atoms behave in solids, liquids, and gases. Quantum statistical mechanics describes how quantum mechanical particles distribute among available energy states, determining thermal properties, phase transitions, and the emergence of collective phenomena like superconductivity and superfluidity. Quantum chromodynamics reveals that even protons and neutrons, which make up atomic nuclei, are composed of more fundamental particles called quarks held together by quantum mechanical forces. The strong nuclear force that binds nuclei emerges from quantum field interactions between quarks, showing that quantum mechanics operates at every level of matter structure. Understanding quantum mechanics reveals that the question, "Why is matter solid?" requires a complete reconceptualization of what we mean by solid. Matter isn't solid because it consists of solid objects packed together, but because quantum mechanical principles create stable, organized patterns of probability and force that resist change and deformation. The solidity we experience emerges from quantum mechanical rules that govern how particles can and cannot behave. These quantum mechanical foundations of matter, S-structure, lead directly to a remarkable consequence. Despite feeling like you constantly touching solid objects, quantum mechanics proves that you never actually touch anything. The resistance you feel when you press against surfaces isn't contact between solid objects, but quantum mechanical barriers that create impenetrable force fields across empty space. Chapter 6. Touching nothing. Every tactile sensation you've ever experienced, from the gentle touch of another person's hand to the solid resistance of a wall, is an elaborate illusion created by forces operating across empty space. You have never actually touched anything in your entire life, despite your brain interpreting electromagnetic and quantum mechanical interactions as direct physical contact. This revelation fundamentally challenges our most basic assumptions about physical reality and our relationship to the material world. When you reach out and touch a table, what actually happens operates on principles that seem to belong more to science fiction than everyday reality. The electrons in your fingertips approach the electrons in the table's surface until electromagnetic repulsion creates a barrier that feels like solid contact. But this barrier exists in empty space between electron clouds. There is no physical intersection between the matter in your finger and the matter in the table. Dr. Richard Feynman illustrated this concept with characteristic insight. When you touch something, you're feeling the electromagnetic force. You never actually make contact. The sensation of touch is electromagnetic fields pushing back against other electromagnetic fields across space that is almost entirely empty. It is remarkable that this feels so much like direct contact that humans evolved with no intuitive understanding of what is really happening. The physics of this non-contact contact operates through what scientists call the contact force, which is actually electromagnetic repulsion between electron clouds. As your finger approaches a surface, the electron probability clouds around atoms in your skin overlap with electron clouds in the surface material. The Pauli exclusion principle prevents these electron clouds from occupying the same space, creating repulsive forces that halt your finger's motion. This electromagnetic barrier develops over distances measured in angstroms units so small that 10 billion angstroms equal 1 meter. Your finger stops moving not because it encounters a solid object, but because electromagnetic forces across this tiny gap become strong enough to balance the pressure you reapply. The actual separation between your finger and the table occurs at scales far too small for your nervous system to detect. Dr. Walter Lewin at MIT calculated that typical contact forces involve electromagnetic fields strong enough to accelerate electrons to significant fractions of the speed of light, yet these enormous forces operate across gaps so small they're impossible to perceive directly. Your brain interprets this electromagnetic interaction as touching a solid surface because evolution programmed your nervous system to translate electromagnetic barriers into the sensation of physical contact. The speed at which contact occurs reveals its electromagnetic nature. When you quickly tap a surface, electromagnetic forces adjust to your finger's motion at the speed of light, roughly 300 million meters per second. Your nervous system, which transmits signals at speeds of only 100 to 120 meters per second, can't process information fast enough to distinguish electromagnetic interaction from direct contact. Temperature affects the sensation of contact by changing the vibrational energy of atoms in materials, which influences how their electron clouds interact with electron clouds in your skin. Hot objects feel hot because their energetic electron clouds interact more vigorously with electrons in your nerve endings. Cold objects feel cold because their less energetic electron clouds interact more weakly, allowing heat to transfer from your warmer skin through electromagnetic interactions. The texture you feel when touching different materials results from how electron clouds in those materials are arranged and how they interact with electron clouds in your skin. Smooth surfaces have regularly arranged electron clouds that create uniform electromagnetic interactions. Rough surfaces have irregularly arranged electron clouds that create varying electromagnetic forces as you move across them. Dr. Jacob Israelachveli at UC Santa Barbara has measured contact forces with precision instruments that can detect interactions between individual molecules. His research confirms that even at the molecular level, what we call contact involves electromagnetic forces operating across measurable gaps. No actual overlap of matter occurs even when contact forces reach their maximum strength. The adhesive forces that make some materials sticky also operate through electromagnetic interactions across empty space rather than through direct contact. Van der Waals forces, hydrogen bonding, and electrostatic attraction can create electromagnetic interactions strong enough to hold objects together without any actual touching between their constituent atoms. This non-contact nature of touch has profound implications for understanding friction between surfaces. When objects slide against each other, friction results from electromagnetic interactions between electron clouds at surface boundaries. The energy dissipated as heat during friction comes from electromagnetic work done as electron clouds in one material interact with electron clouds in another across tiny gaps. Modern atomic force microscopes exploit the electromagnetic nature of contact to feel individual atoms without touching them. These instruments use tiny cantilever probes that detect electromagnetic forces between the probe tip and surface atoms. By measuring these forces, scientists can map surface structure with atomic scale precision while maintaining separation distances measured in nanometers. The phenomenon of non-contact touch extends beyond simple mechanical interactions to influence how we understand tool use and object manipulation. When you write with a pen, electromagnetic forces between electron clouds in your fingers interact with electron clouds in the pen across tiny gaps. The pen responds to these forces and transmits them through electromagnetic interactions with paper molecules, creating marks without any direct contact between matter. Dr. Mark Rutland at the Royal Institute of Technology has studied how contact forces vary with surface chemistry and molecular structure. His research reveals that the sensation of touching different materials involves complex patterns of electromagnetic interaction that depend on molecular geometry, electron distribution, and quantum mechanical effects operating across interfaces. The liquid nature of water creates unique contact sensations because water molecules can flow and rearrange their electromagnetic interactions continuously. When you put your hand in water, you're not touching the water, but experiencing changing patterns of electromagnetic interaction as water molecules move around your fingers and their electron clouds create varying repulsive forces. Understanding non-contact touch helps explain why some materials feel different, even when they have similar surface textures. Cotton and silk may have similar physical structures, but create different tactile sensations because their different molecular compositions produce different patterns of electromagnetic interaction with electron clouds in human skin. The role of moisture in contact sensations demonstrates how electromagnetic interactions change with environmental conditions. Humid air contains water molecules that create additional electromagnetic interactions between your skin and other surfaces. This explains why materials feel different in humid versus dry conditions and why some textures are more noticeable when your skin is moist. Dr. Susan Lederman at Queen's University has studied how the human nervous system processes electromagnetic interactions to create the sensation of touch. Her research reveals that specialized nerve endings in human skin are optimized to detect specific patterns of electromagnetic force that correspond to different material properties like hardness, texture, and temperature. The fact that you never actually touch anything has philosophical implications that extend beyond physics. Every caress, handshake, embrace, or gentle touch that feels like direct human connection actually involves electromagnetic forces operating across empty space. Physical intimacy is really electromagnetic intimacy, the interaction of force fields rather than the contact of solid matter. This realization doesn't diminish the significance of touch, but rather reveals its true nature as one of the most sophisticated forms of electromagnetic communication possible. When someone touches you gently, their electromagnetic fields are interacting with yours in precisely controlled ways that convey information about pressure, movement, temperature, and emotion through quantum mechanical and electromagnetic processes. The evolutionary development of touch sensors in human skin represents millions of years of optimization for interpreting electromagnetic interactions as meaningful information about the environment. Your brain's ability to distinguish between soft and hard, warm and cold, smooth and rough depends entirely on its capacity to process different patterns of electromagnetic force across gaps you cannot perceive. Modern virtual reality and haptic feedback technologies attempt to recreate touch sensations by generating electromagnetic forces that simulate the patterns your skin would experience when interacting with different materials. These technologies work precisely because touch is already electromagnetic interaction. They simply substitute artificial electromagnetic fields for the natural fields produced by material surfaces. Understanding that you never actually touch anything transforms how you think about your relationship with the physical world. Every object you've ever held, every surface you've ever leaned against, every person you've ever embraced has remained separated from you by the fundamental forces and quantum mechanical principles that govern matter. Yet these same forces create the rich, detailed sensory world that makes physical existence meaningful and beautiful. The revelation that touch is electromagnetic illusion leads to an even more remarkable question. If electromagnetic repulsion prevents actual contact between matter, what determines which materials can pass through each other and which cannot? The answer reveals yet another layer of the complex relationship between empty space and solid reality. Chapter 7. Material Properties. The vast differences between materials. Why diamond is harder than graphite despite both being pure carbon. Why copper conducts electricity while rubber insulates. Why glass is transparent while metal is opaque. All emerge from different ways that mostly empty atoms arrange their electron clouds and electromagnetic interactions. These material properties aren't determined by how much empty space atoms contain, since all atoms are equally empty, but rather by how that empty space is organized and how electromagnetic forces operate within it. Diamond and graphite provide the most striking example of how atomic arrangement in empty space determines material properties. Both materials consist entirely of carbon atoms with identical nuclear structure and electron configurations. Yet diamond is the hardest natural material known, while graphite is so soft you can write with it. The difference lies not in the atoms themselves, but in how they organize their electron clouds in three-dimensional space. In diamond, each carbon atom uses its 4 outer electrons to form covalent bonds with 4 neighboring carbon atoms, creating a three-dimensional network where electron clouds are shared in tetrahedral patterns throughout the crystal structure. This arrangement distributes electromagnetic forces uniformly in all directions, making diamond extremely resistant to deformation. When you try to scratch diamond, you're attempting to break these uniformly distributed electromagnetic bonds simultaneously across multiple directions. Dr. Richard Smalley at Rice University showed that graphite as layered structure creates entirely different electromagnetic interactions despite using identical carbon atoms. In graphite, carbon atoms form strong bonds within flat sheets, but these sheets are held together only by weak van der Waals forces between their electron clouds. This allows the sheets to slide past each other easily while maintaining strong internal structure within each layer. The electromagnetic basis of material hardness extends beyond carbon structures to explain hardness in all materials. Hardness measures resistance to deformation, which ultimately depends on how much energy is required to reorganize electron clouds when materials are stressed. Materials with electron clouds organized in rigid, uniformly bonded networks resist deformation better than materials with more flexible bonding patterns. Electrical conductivity provides another dramatic example of how electron cloud organization determines material properties. In metals like copper, some electrons exist in conduction bands, energy states that allow electrons to move freely throughout the material's crystal structure. These mobile electrons can respond to electromagnetic fields by flowing as electrical current through the mostly empty atomic lattice. Dr. Felix Bloch's quantum mechanical theory of electrical conduction explains that metallic conductivity emerges when electron clouds overlap to create continuous pathways for electron flow. The empty space between atomic nuclei doesn't impede electrical conduction. Instead, it provides the medium through which electrons can move when their wave functions extend throughout the metallic structure. Electrical insulators like rubber or glass have electron clouds tightly bound to individual atoms, creating energy gaps that prevent electrons from moving freely. In these materials, electrons remain localized around specific nuclei rather than forming the delocalized electron clouds that enable metallic conduction. The same empty space exists in insulators as in conductors, but electron cloud organization prevents current flow. Semiconductors like silicon represent an intermediate case where electron cloud organization can be modified by temperature, electric fields, or chemical dopants. At low temperatures, silicon behaves like an insulator because thermal energy isn't sufficient to excite electrons into conduction bands. At higher temperatures, thermal energy promotes some electrons to conducting states, creating modest electrical conductivity. The optical properties that make materials transparent, opaque, or colored also result from how electron clouds interact with electromagnetic radiation. When light encounters a material, it interacts with electron clouds in ways that depend on both the light's frequency and the material's electronic structure. Transparent materials, Like glass have electron clouds organized, so the visible light photons don't have sufficient energy to excite electrons to higher energy states. The light passes through the material without being absorbed because no electron transitions are available at visible light frequencies. The transparency isn't due to large empty spaces between atoms, but rather due to electron energy levels that don't match visible light energies. Dr. Philip Anderson's work on localized electronic states explains how small changes in electron cloud organization can dramatically alter optical properties. Adding trace amounts of chromium to aluminum oxide creates ruby, which appears red because chromium's electron clouds absorb blue and green light while allowing red light to pass through or be reflected. Metallic opacity results from the same mobile electron clouds that enable electrical conduction. Free electrons in metals can absorb electromagnetic radiation at any frequency by converting photon energy into kinetic energy. This strong interaction between light and mobile electron clouds makes metals generally opaque while giving them characteristic metallic luster. The mechanical properties of elasticity and plasticity also depend on electron cloud arrangements and how they respond to applied forces. Elastic materials return to their original shapes after deformation because their electron cloud patterns naturally restore the equilibrium atomic arrangements when stress is removed. Plastic materials undergo permanent deformation because applied forces reorganize their electron clouds into new stable configurations. Dr. John Nye at Bristol University developed a mathematical framework for understanding how crystal structure influences mechanical properties. His work shows that elastic constants, measures of how materials respond to different types of stress, can be calculated directly from electron cloud arrangements and the electromagnetic forces between them. Temperature effects on material properties result from how thermal energy affects electron cloud behavior. Higher temperatures increase atomic vibrations, which changes average distances between electron clouds and can alter bonding patterns. This explains why materials expand when heated and why many properties like electrical conductivity and mechanical strength vary with temperature. Phase transitions between solid, liquid, gas, and plasma states represent dramatic reorganizations of electron cloud arrangements. In solids, electron clouds maintain fixed relationships that preserve long-range order. In liquids, electron clouds maintain local bonding but allow atomic rearrangement. In gases, electron clouds interact only during brief collisions. In plasmas, thermal energy completely separates electrons from nuclei. The magnetic properties of materials provide another example of how electron cloud organization determines behavior. Ferromagnetic materials like iron have electron clouds arranged so that electron spins align in the same direction across large regions, creating strong magnetic fields. Diamagnetic materials have electron clouds that respond to external magnetic fields by creating opposing magnetic moments. Dr. Louise Neal's work on magnetic domains shows how electron cloud arrangements create complex magnetic structures even within single materials. These domains represent regions where electron spins are aligned, separated by boundaries where spin orientations gradually change. The size and arrangement of magnetic domains determine a material's overall magnetic behavior. Chemical reactivity depends on electron cloud arrangements in outer atomic shells. Materials with electron clouds that can easily form bonds with other atoms tend to be chemically reactive, while materials with stable, complete electron shell configurations tend to be chemically inert. Noble gases have electron cloud configurations that resist chemical bonding, making them largely unreactive under normal conditions. Catalytic materials have electron cloud arrangements that lower energy barriers for chemical reactions without being consumed in the process. Platinum's electron clouds can interact with reactant molecules in ways that facilitate bond breaking and formation, explaining its effectiveness as a catalyst for numerous chemical processes. The study of material properties at extreme conditions reveals how electron cloud arrangements respond to high pressures, temperatures, and electromagnetic fields. Under extreme compression, electron clouds can be forced into overlapping configurations that create entirely new material phases with properties unlike anything observed under normal conditions. Dr. Russell Hemley at Carnegie Institution has used diamond anvil cells to compress materials to pressures exceeding those found in planetary cores. His research reveals that extreme pressure can force electron clouds into arrangements that make normally insulating materials become metallic conductors or create new crystal structures with unprecedented hardness. Understanding material properties in terms of electron cloud organization helps explain why the search for new materials often focuses on controlling atomic arrangements rather than discovering new types of atoms. The same chemical elements can create vastly different materials depending on how their electron clouds are organized in space. Modern materials science increasingly uses computational methods to predict material properties from electron cloud calculations before synthesizing new materials experimentally. These quantum mechanical simulations can predict hardness, conductivity, optical properties, and other characteristics by calculating how electron clouds will interact in proposed crystal structures. The relationship between electron cloud organization and material properties reveals that the incredible diversity of material behavior around us emerges not from different types of fundamental matter, but from different ways of organizing electromagnetic interactions in mostly empty space. Every useful material property represents a solution to the challenge of arranging electron clouds to create desired electromagnetic behaviors within atomic emptiness. This understanding leads to a profound realization. If material properties emerge from electromagnetic organization in empty space, what happens when we examine matter under extreme conditions that can overcome these electromagnetic barriers? The answer reveals phenomena that challenge our basic concepts of solidity and emptiness. Chapter 8. Extreme conditions under extreme conditions of pressure, temperature, and electromagnetic fields. The familiar rules that make matter feel solid break down completely, revealing states of existence where the boundary between empty space and solid matter becomes meaningless. These extreme environments, found inside stars, particle accelerators, and laboratory experiments, demonstrate that the solidity we experience in everyday life is just one temporary arrangement of forces that can be completely reorganized under different conditions. The most dramatic example occurs inside neutron stars, where gravitational pressure becomes so intense that electromagnetic forces can no longer maintain normal atomic structure. In these cosmic laboratories, pressures reach 100 trillion times greater than atmospheric pressure on Earth, squeezing matter to densities where a teaspoon would weigh 6 billion tons. Under such conditions, the empty space within atoms completely collapses. Dr. Gordon Baim at the University of Illinois has calculated what happens during this collapse. As pressure increases, electron clouds are forced closer to atomic nuclei until electrons and protons combine to form neutrons. The electromagnetic repulsion that normally maintains atomic emptiness becomes insufficient to resist gravitational compression, and matter transitions to a state where nuclear particles touch directly rather than being separated by mostly empty atomic structure. In neutron star material, the 99.999999999999996% emptiness of normal atoms disappears entirely. The resulting matter has nuclear density throughout, roughly 100 trillion times denser than water. A cubic centimeter of neutron star material contains as much mass as Mount Everest, demonstrating what happens when the electromagnetic forces that create atomic emptiness are completely overwhelmed. But neutron stars represent just one example of how extreme conditions can eliminate the emptiness of normal matter. Inside the cores of massive stars, temperatures reach 100 million Kelvin, hot enough that thermal energy completely strips electrons from atomic nuclei, creating a state called plasma, where matter exists as a sea of separated nuclei and free electrons. Dr. David Arnett at the University of Arizona studies stellar nucleosynthesis, the process by which extreme temperatures and pressures inside stars create heavy elements through nuclear fusion. In stellar cores, thermal energy is so intense that electromagnetic repulsion between atomic nuclei can be overcome, allowing nuclear particles to get close enough for the strong nuclear force to bind them together into heavier elements. These fusion reactions demonstrate another way extreme conditions can eliminate atomic emptiness. When hydrogen nuclei fuse to form helium, the electromagnetic barriers that normally keep nuclei separated by vast empty spaces are overcome by enormous kinetic energy. The resulting helium nucleus occupies much less space than the original separated hydrogen nuclei, effectively converting empty space into binding energy according to Einstein's E equals mc. Particle accelerators, like the Large Hadron Collider, create even more extreme conditions by accelerating particles to energies comparable to those present just after the Big Bang. When these ultra-high energy particles collide, they recreate conditions where normal concepts of matter and empty space break down completely, revealing the fundamental quantum fields that underlie all physical reality. Dr. John Ellis at CERN describes these collisions as creating temporary states where the vacuum itself becomes unstable, spawning particle-antiparticle pairs from what we normally consider empty space. In these extreme conditions, the distinction between matter and vacuum disappears as quantum field fluctuations create and destroy particles on timescales measured in yoctoseconds, units so brief that light travels less than the diameter of a proton. The quark-gluon plasma created in heavy ion collisions represents a state of matter where even protons and neutrons lose their identity. At temperatures over 2 trillion Kelvin, nuclear particles melt into their constituent quarks and gluons, creating a liquid-like state where the fundamental building blocks of matter flow freely without being bound into recognizable particles. Laboratory experiments using diamond anvil CELLS can reach some stellar conditions by compressing materials to pressures exceeding 500 gigapascals, over 5 million times atmospheric pressure. Dr. Russell Hemley at Carnegie Institution has used these devices to study how electron cloud arrangements change under extreme compression. His research reveals that extreme pressure can force normally insulating materials to become metallic conductors, as their electron clouds are compressed into overlapping configurations that allow electrical current flow. Hydrogen, normally an insulating gas, becomes a metallic conductor under pressures found inside Jupiter's core, demonstrating how extreme conditions can completely transform material properties. The metallic hydrogen state illustrates how extreme pressure can eliminate the energy gaps that normally separate electron energy levels in atoms. When electron clouds are compressed sufficiently, discrete energy levels merge into continuous conduction bands, allowing electrons to move freely throughout the material structure, even though individual atoms maintain their nuclear identity. Magnetic fields provide another way to create extreme conditions that alter the relationship between matter and empty space. In magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's electromagnetic forces become so intense that they can affect the vacuum itself, creating virtual particle pairs and modifying the properties of empty space. Dr. Christopher Thompson at the Canadian Institute for Theoretical Astrophysics has studied how ultra-strong magnetic fields can polarize the vacuum, creating directional properties in what we normally consider empty space. These fields are strong enough to distort atomic structure, making atoms become elongated in the direction of the magnetic field and creating matter with properties unlike anything possible under normal conditions. The study of matter under extreme electric fields reveals similar modifications to atomic structure. When electric field strengths approach Yp volts per meter, the field strength that would tear electrons from atomic nuclei. Normal atomic structure becomes impossible to maintain. The Schwinger limit describes the field strength at which empty space itself becomes unstable and begins producing particle-antiparticle pairs. Laser technology is approaching intensities where such extreme electric fields become possible in laboratory settings. Ultra-intense laser pulses can create electromagnetic field strengths comparable to those found inside atoms, allowing scientists to study how matter behaves when the electromagnetic forces that maintain atomic structure are challenged by external fields of similar magnitude. Dr. Gerard Mourou, Nobel laureate for his work on laser intensity, has predicted that future laser systems will reach intensity sufficient to create electron-positron pairs directly from vacuum, demonstrating that empty space contains potential energy that can manifest as real particles under sufficiently extreme conditions. The phenomenon of Hawking radiation around black holes represents perhaps the most extreme example of how matter and empty space can interconvert. According to Stephen Hawking's calculations, quantum fluctuations near black hole event horizons can separate virtual particle pairs, allowing one particle to escape while the other falls into the black hole. This process converts vacuum energy into real particles, demonstrating that even empty space contains latent matter. Understanding matter under extreme conditions reveals that the solidity we experience results from a delicate balance of forces that can be completely disrupted when conditions become sufficiently extreme. The electromagnetic repulsion that prevents atomic collapse, the quantum pressure that maintains atomic size, and the energy gaps that determine material properties all depend on environmental conditions remaining within certain bounds. When temperature, pressure, or electromagnetic field strength exceed these bounds, matter can transition to states where normal concepts of solidity and emptiness no longer apply. Nuclear matter, quark-gluon plasma, metallic hydrogen, and vacuum polarization represent different solutions to organizing matter and energy under conditions where the rules governing normal atomic structure break down. These extreme states also provide insights into cosmic evolution and the formation of the universe itself. The Big Bang likely involved conditions so extreme that normal atomic structure was impossible, with matter existing in exotic states that have no counterpart in contemporary experience. Understanding these extreme matter states helps cosmologists model how the universe evolved from its earliest moments to the relatively moderate conditions that allow atoms, chemistry, and biology to exist. The relationship between extreme conditions and matter states also has practical implications for energy production and material science. Nuclear fusion requires creating conditions extreme enough to overcome electromagnetic repulsion between nuclei, while materials research seeks to understand how extreme pressure or temperature can create new materials with unprecedented properties. Modern condensed matter physics increasingly studies artificial extreme conditions created using ultra-fast laser pulses, high magnetic fields, and novel compression techniques. These experiments reveal that matter has far more possible states than the familiar solid, liquid, gas, and plasma phases, with new states emerging when specific combinations of extreme conditions are achieved. The exploration of matter under extreme conditions ultimately demonstrates that the question, "Why is matter solid?" depends entirely on the environmental context. Under normal conditions, electromagnetic and quantum mechanical forces create the organized emptiness we experience as solid matter. But under extreme conditions, these same forces can be overwhelmed, reorganized, or supplemented by other effects that create entirely different relationships between matter, energy, and space. This contextual nature of solidity leads to a deeper question. What does it mean for something to be real when matter can exist in so many different states depending on conditions? The answer requires examining the fundamental nature of reality itself. Chapter 9. The nature, The discovery that atoms are mostly empty space while matter feels solid forces us to confront fundamental questions about the nature of reality itself. What does it mean for something to be real when everything we can touch and see consists almost entirely of nothing? How do we reconcile our direct sensory experience of a solid world with scientific knowledge that this world is overwhelmingly empty space organized by invisible forces? This paradox challenges the most basic assumptions humans make about existence. For thousands of years, philosophers and scientists assumed that matter was substantial, that objects possess inherent solidity that explains why they feel solid when we touch them. The revelation that matter is almost entirely empty space, held together by electromagnetic forces and quantum mechanical principles, requires a complete reconceptualization of what we mean by real and solid. Dr. Carlo Rovelli at the Centre de Physique Théorique describes this as the difference between manifest reality, what we directly observe and experience, and scientific reality, what scientific investigation reveals about the underlying structure of the world. These two realities appear completely contradictory. Manifest reality is a world of solid objects, while scientific reality is a world of mostly empty space organized by abstract forces. The resolution lies in understanding that what we call solidity is not a fundamental property of matter, but rather an emergent phenomenon that arises from the complex interactions of forces operating in mostly empty space. Solidity is real as an experience, but it emerges from underlying processes that don't themselves possess the quality of solidity. This concept of emergence is crucial for understanding how emptiness creates solidity. Emergence occurs when collections of simple components interacting according to basic rules produce complex behaviors that the individual components don't possess. Consciousness emerges from neurons that aren't themselves conscious. Wetness emerges from water molecules that aren't themselves wet. Solidity emerges from atoms that aren't themselves solid. Dr. Philip Anderson, Nobel laureate in physics, articulated this principle with his famous observation that more is different. He showed that understanding the components of a system doesn't automatically provide understanding of how those components behave when organized into larger structures. The solid properties of matter can't be deduced simply from knowing that atoms are mostly empty space. They emerge from the collective electromagnetic and quantum mechanical interactions of vast numbers of atoms. The philosophical implications extend beyond physics to challenge basic categories of thought about substance and properties. If matter isn't substantial in the way our senses suggest, what can we say about the nature of physical reality? Are we living in a universe that's fundamentally insubstantial, where everything solid is really an elaborate illusion created by force patterns in empty space? Some interpretations of quantum mechanics suggest an even more radical view, that reality itself doesn't exist independently of observation and measurement. According to the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg, quantum systems don't have definite properties until they're measured. This would mean that the solidity we experience only becomes real when we interact with matter through measurement or touch. Dr. John Wheeler explored these implications in his concept of it from bit, the idea that reality emerges from information rather than existing as fundamental substance. Wheeler suggested that what we call matter might be better understood as self-consistent patterns of information that create the appearance of substance through their organizational structure. The many worlds interpretation of quantum mechanics, developed by Hugh Everett III, offers a different perspective on the nature of reality. This interpretation suggests that all possible quantum outcomes actually occur, but in separate parallel universes. In this view, the solid matter we experience represents just one branch of reality among infinite parallel branches where matter might have different properties or organizational principles. Information theory provides another lens for understanding how emptiness can create apparently solid reality. The amount of information required to specify the quantum state of all particles in a macroscopic object is enormous, far more information than could be stored in the physical volume those particles occupy. This suggests that material objects might be better understood as information structures rather than collections of substantial particles. Dr. Anton Zeilinger at the University of Vienna has demonstrated quantum phenomena that support an information-based view of reality. His experiments with quantum entanglement and teleportation show that quantum information can be transferred between particles without any physical substance moving between them. This suggests that information, rather than substance, might be the fundamental constituent of reality. The holographic principle in physics proposes that all information contained in a volume of space can be encoded on the boundary of that volume, like a hologram storing three-dimensional information on a two-dimensional surface. This principle suggests that reality might be fundamentally two-dimensional, with three-dimensional experience emerging from information patterns projected from cosmic boundaries. Dr. Leonard Susskind at Stanford University has explored how holographic principles might explain the nature of space and matter. His work suggests that the three-dimensional space we experience, including the emptiness within atoms, might be an emergent property of information encoded on distant two-dimensional surfaces. These perspectives don't diminish the reality of our experience, but rather expand our understanding of what reality might mean. The chair you're sitting in is genuinely solid in the sense that electromagnetic forces create genuine resistance to compression and motion. The solidity is real as a macroscopic phenomenon, even though it emerges from mostly empty atomic structures governed by quantum mechanical principles. The relationship between emptiness and solidity also illuminates the role of scale in determining the nature of reality. At atomic scales, matter is mostly empty space organized by quantum mechanical forces. At macroscopic scales, these quantum mechanical forces create electromagnetic barriers that feel solid. At cosmic scales, even the densest matter is mostly empty space between stars and galaxies. Dr. Sean Carroll at Caltech argues that these different scales represent different levels of description rather than different levels of reality. Atomic scale emptiness and macroscopic solidity are both equally valid descriptions of the same underlying physical system, appropriate for different purposes and contexts. The question of what makes something real becomes even more complex when considering virtual particles and quantum field fluctuations. Quantum field theory describes empty space as filled with virtual particles that briefly appear and disappear, borrowing energy from the vacuum and repaying it so quickly that their existence can't be directly observed. These virtual particles have measurable effects on atomic structure and electromagnetic forces, making them real in terms of their consequences, even though they're unobservable in principle. The study of emergence in complex systems provides additional insights into how macroscopic properties can arise from microscopic components that don't possess those properties. Superconductivity emerges from electron interactions in materials whose individual atoms aren't superconducting. Magnetism emerges from quantum mechanical spin interactions between particles that don't themselves possess macroscopic magnetic properties. Dr. Robert Laughlin, Nobel laureate for his work on emergence in condensed matter physics, argues that emergent phenomena are more fundamental than the microscopic components from which they emerge. According to this view, the solidity of matter is more real than the atomic emptiness from which it emerges, because solidity is what we can actually observe and measure directly. The nature of space itself remains one of the deepest questions in physics. Is space simply an empty stage on which matter performs, or does space have its own structure and properties? General relativity treats space and time as dynamic entities that can curve and change. Quantum field theory suggests that space is filled with quantum fields whose fluctuations create all particles and forces. loop quantum gravity, and string theory offer different perspectives on the fundamental nature of space, matter, and their relationship. These theories suggest that space itself might be quantized, composed of discrete units rather than being continuous, and that what we call empty space might have complex internal structure at scales far smaller than atoms. Understanding the relationship between atomic emptiness and macroscopic solidity reveals that the nature of reality is far richer and more subtle than our everyday experience suggests. We live in a universe where emptiness and solidity, wave and particle, discrete and continuous, virtual and real, represent different aspects of a deeper unity that transcends these apparent contradictions. The fact that mostly empty atoms can create genuinely solid experience demonstrates that reality operates through principles more beautiful and complex than simple substance. Forces, fields, information, and organization create the rich, detailed world we inhabit from ingredients that individually don't possess the properties of that world. This understanding transforms rather than eliminates the wonder of physical existence. The solid world around us becomes more remarkable, not less, when we understand it as an emergent masterpiece created by quantum mechanical and electromagnetic forces operating across vast empty spaces with mathematical precision. Chapter 10. Universal Principles. The revelation that atomic emptiness creates macroscopic solidity through electromagnetic and quantum mechanical principles connects our everyday experience to the most fundamental laws governing the entire universe. The same forces that prevent your hand from passing through a wall also determine the structure of stars, the formation of galaxies, and the ultimate fate of cosmic evolution. Understanding how emptiness becomes solidity reveals universal principles that operate from the quantum scale to the cosmic scale with remarkable consistency. The electromagnetic force that creates contact sensations between electron clouds is one of four fundamental forces that govern all interactions in the universe. Along with gravity, the strong nuclear force, and the weak nuclear force, electromagnetism shapes everything from subatomic particle behavior to the large-scale structure of space and time. The solidity you feel when touching objects represents your direct, personal experience of one of the universe's most basic organizing principles. Dr. Steven Weinberg's work on the unification of fundamental forces reveals that electromagnetism and the weak nuclear force are actually different aspects of a single electroweak force that becomes apparent only at extremely high energies. This unification suggests that the electromagnetic interactions creating everyday solidity are connected to the nuclear processes that power stars and create heavy elements through cosmic evolution. The same Pauli exclusion principle that prevents electron clouds in your fingertips from occupying the same space as electron clouds in objects you touch also determines the internal structure of neutron stars and white dwarf stars. When stellar cores collapse under gravity, the exclusion principle creates degeneracy pressure that can halt gravitational collapse, creating stable stellar remnants supported by quantum mechanical principles identical to those that maintain atomic structure. Dr. Subramanian Chandrasekhar calculated that white dwarf stars are supported against gravitational collapse by electron degeneracy pressure, the same quantum mechanical effect that prevents electrons in ordinary atoms from falling into their nuclei. This connection demonstrates how quantum principles operating within atoms scale up to determine the fate of entire stars across cosmic time. The conservation of energy that governs electromagnetic interactions and atomic contact forces also operates throughout cosmic evolution, from the Big Bang to the heat death of the universe. Energy can neither be created nor destroyed, only transformed from one form to another. When you feel the solid resistance of matter, you are experiencing energy stored in electromagnetic fields being converted into kinetic energy of moving particles in your nervous system. This energy conservation connects atomic scale phenomena to cosmic scale processes. the nuclear fusion reactions that power stars convert nuclear binding energy into electromagnetic radiation according to Einstein's E=mc. The same relationship between mass and energy that governs these cosmic processes operates in the atomic nuclei that anchor electron clouds in all matter, including the matter composing your body. Quantum mechanics, which determines electron cloud behavior and atomic structure, also governs the behavior of the entire universe at its earliest moments. The quantum fluctuations that create uncertainty in electron positions around atomic nuclei are the same type of fluctuations that, when amplified by cosmic inflation, created the density variations that eventually became galaxies, stars, and planets. Dr. Alan Guth's theory of cosmic inflation describes how quantum mechanical fluctuations in the early universe's vacuum energy created the large-scale structure we observe today. The same quantum principles that prevent atoms from collapsing into nuclear density also created the cosmic web of dark matter and ordinary matter that forms the scaffolding for all cosmic structure. The relationship between force and field that creates electromagnetic contact interactions also operates throughout the cosmos via gravity. Just as electromagnetic fields create forces between electron clouds across empty space, gravitational fields create forces between masses separated by vast cosmic distances. The mathematical structure underlying both types of field interactions follows similar principles derived from fundamental symmetries of space and time. General relativity reveals that gravity, like electromagnetism, operates through field effects rather than direct contact. Massive objects curve spacetime, and other objects follow the straightest possible paths through this curved spacetime. This gravitational field effect is conceptually similar to how electromagnetic fields create apparent contact forces between atoms. Both involve action at a distance through empty space rather than mechanical contact between solid objects. The thermodynamic principles that govern how matter responds to temperature changes operate at every scale, from atomic vibrations to stellar evolution to cosmic expansion. The relationship between temperature and atomic motion that makes materials expand when heated also determines stellar structure, planetary formation, and the ultimate cooling of the universe as it expands. Dr. Roger Penrose has explored how thermodynamic principles connect the microscopic arrow of time experienced in atomic processes to the macroscopic arrow of time that governs cosmic evolution. The same increase in entropy that makes electromagnetic interactions between atoms irreversible also drives the universe's evolution, from ordered initial conditions toward maximum entropy in the far future. Symmetry principles that determine allowed electron configurations around atomic nuclei also govern the fundamental forces and particle interactions throughout the universe. The mathematical symmetries underlying quantum mechanics and electromagnetic theory are the same symmetries that govern the standard model of particle physics and potentially unify all fundamental forces. The concept of spontaneous symmetry breaking, which explains how particles acquire mass through interactions with the Higgs field, operates through principles similar to those that determine how electron clouds arrange themselves around nuclei to minimize energy. Both phenomena involve systems settling into stable configurations that break the symmetries of their underlying governing equations. Dr. Frank Wilczek's work on asymptotic freedom shows how the strong nuclear force that binds atomic nuclei follows principles related to electromagnetic interactions, but with inverted behavior. Nuclear forces get stronger at longer distances, while electromagnetic forces get weaker. This complementary behavior suggests deep connections between different fundamental forces that may reflect an underlying unified structure. The scaling laws that govern how atomic properties change with nuclear charge also appear in cosmic structure formation, stellar evolution, and galactic dynamics. Power law relationships that describe electron binding energies and atomic sizes have mathematical Analogs in the relationships between stellar mass and luminosity, between galactic mass and rotation curves, and between cosmic structure size and formation time. Information theory provides another universal principle connecting atomic structure to cosmic evolution. The information required to specify the quantum state of electrons around a nucleus is related to the entropy of that system. Similarly, the information required to specify the state of cosmic structure reflects the entropy evolution of the universe as a whole. Dr. Jacob Bekenstein's work on black hole thermodynamics reveals that even gravity follows thermodynamic and information theoretic principles similar to those governing atomic structure. Black hole entropy depends on surface area rather than volume, suggesting holographic principles that may apply to information storage throughout the universe. The uncertainty principle that governs electron behavior in atoms also applies to cosmic phenomena through quantum field theory. Virtual particle creation and vacuum fluctuations operates by the same uncertainty relationships that prevent electrons from having definite positions and velocities simultaneously. These quantum uncertainties may have played crucial roles in cosmic inflation and the creation of cosmic structure. The wave-particle duality that makes electrons behave as both particles and waves also applies to light, which exhibits both electromagnetic wave properties and photon particle properties. This duality extends to all quantum fields, suggesting that the wave-like nature of matter at atomic scales reflects fundamental properties of reality at all scales. Modern cosmology increasingly recognizes that the universe as a whole may be governed by quantum mechanical principles similar to those operating within atoms. The concept of cosmic decoherence suggests that the classical behavior of large-scale cosmic structure emerges from underlying quantum processes through environmental interactions, just as classical atomic behavior emerges from quantum electron dynamics. The anthropic principle in cosmology suggests that the fundamental constants governing electromagnetic and nuclear forces must have values compatible with the existence of atoms, chemistry, and life. If electromagnetic coupling were significantly different, electron clouds would either be too tightly bound to nuclei or too weakly bound to create stable atoms. The universe we observe may be one of many possible universes, distinguished by having physical constants that permit the emergence of complex structure from atomic scale interactions. Understanding the universal principles that connect atomic emptiness to cosmic structure reveals that asking, "Why is matter solid?" leads directly to the deepest questions about the nature of reality itself. The electromagnetic and quantum mechanical forces that create the illusion of solidity in mostly empty atoms are the same forces that shape cosmic evolution and may determine whether universes can exist with complex structure and conscious observers. The solid world you experience through touch and vision represents your direct sensory contact with fundamental forces that operate throughout the cosmos. When you feel the resistance of matter, you're experiencing the same electromagnetic principles that govern stellar formation, galactic dynamics, and cosmic evolution. The emptiness within atoms connects to the emptiness of space itself, while the forces that organize atomic emptiness also organize cosmic structure across billions of light years. This cosmic perspective transforms understanding of everyday experience from mundane contact with solid objects to direct participation in universal processes that connect the quantum and cosmic realms through elegant mathematical principles operating across all scales of space and time. Throughout this journey into the heart of matter, we've discovered that the solid world around you is one of the most beautiful illusions in the universe. We've seen how atoms are indeed mostly empty space, vast cosmic voids where football stadium-sized atoms contain marble-sized nuclei, yet create the experience of complete solidity through electromagnetic forces and quantum mechanical principles operating across that emptiness. We've explored how nuclear forces bind particles together with energies millions of times stronger than chemical bonds, creating tiny but incredibly dense anchors around which electron probability clouds can organize into stable patterns. These electron clouds don't orbit like miniature planets, but exist as standing wave patterns that define where electrons might be found, creating the fuzzy boundaries that determine atomic size and behavior. The electromagnetic repulsion between these electron clouds is what you feel every time you touch anything. Your hand has never actually made contact with any object. Instead, electron clouds in your skin interact with electron clouds in surfaces through forces strong enough to stop your motion while maintaining separations measured in angstroms. Every sensation of touch is electromagnetic communication across empty space, rather than mechanical contact between solid objects. We've discovered how quantum mechanics creates the fundamental rules that prevent matter from collapsing despite being mostly empty space. The Heisenberg uncertainty principle ensures that confining electrons to smaller spaces requires enormous kinetic energies, creating quantum pressure that maintains atomic size. The Pauli exclusion principle prevents multiple electrons from occupying the same quantum state, forcing them into layered shells that give atoms their structure and size. These same quantum principles determine all material properties, despite every material being equally empty at the atomic level. Diamond and graphite, both pure carbon, behave completely differently because their electron clouds organize in different three-dimensional patterns. Electrical conductivity, optical transparency, magnetic properties, and mechanical strength all emerge from various ways of organizing electromagnetic interactions in mostly empty atomic space. Under extreme conditions in neutron stars, stellar cores, and particle accelerators, the familiar rules that create solidity from emptiness break down completely. Pressures and temperatures can overcome electromagnetic repulsion and quantum pressure, forcing matter into exotic states where normal concepts of emptiness and solidity no longer apply. These extreme conditions reveal that the solidity we experience depends entirely on environmental context. Perhaps most remarkably, we've seen how these discoveries challenge our fundamental understanding of reality itself. The solid world you experience emerges from, but cannot be reduced to the mostly empty atomic components from which it's built. Solidity is real as an emergent phenomenon, even though it arises from underlying processes that don't themselves possess the quality of solidity. This emergence connects atomic physics to universal principles that govern everything from stellar evolution to cosmic structure formation. The same electromagnetic forces that create contact sensations also power stars and shape galaxies. The same quantum mechanical principles that maintain atomic structure also determine the fate of stellar remnants and may have created the cosmic structure we observe. As you continue through your day after watching this, remember that every step you take, every object you hold, every surface you lean against represents your direct sensory experience of fundamental forces operating throughout the universe. When you feel the solid resistance of matter, you're not touching substantial objects, but experiencing electromagnetic field interactions that connect you to cosmic processes spanning from quantum scales to galactic dimensions. The chair you're sitting in maintains its shape not because it's made of solid stuff, but because trillions of atoms have organized their electron clouds into stable electromagnetic patterns that resist deformation. The screen you're watching displays images by controlling how electron clouds in semiconductor materials interact with photons of light. Your own body processes the energy to understand these concepts through biochemical reactions that depend on electromagnetic interactions between mostly empty atoms. When you look at your hands, consider that they're composed of roughly 1,028 atoms, each one 99.99999999996% empty space, held together by forces operating across gaps you cannot perceive. The apparent solidity of your hands emerges from quantum mechanical and electromagnetic processes that create genuine resistance and structure from ingredients that are almost entirely nothing. This doesn't make your physical existence less real or meaningful. It makes it more remarkable. You are a conscious pattern of electromagnetic organization that has emerged from cosmic emptiness through 13.8 billion years of universal evolution. The forces that create your experience of solid reality also created the stars that forged the heavy elements in your body and the cosmic processes that led to planets, chemistry, and life. The fact that matter feels solid despite being mostly empty space reveals something profound about the nature of reality. Substance emerges from organization rather than from inherent properties of fundamental components. What matters isn't what things are made of, but how they're organized and how they interact. You are not separate from these universal processes. You are a local manifestation of them. The electromagnetic forces that prevent your hand from passing through walls are the same forces that determine stellar structure and galactic formation. The quantum mechanical principles that maintain your atomic structure also operate in the cores of non-neutron stars and in the vacuum fluctuations of empty space. Every breath you take involves quantum mechanical and electromagnetic interactions between trillions of mostly empty atoms that somehow create the seamless experience of life, consciousness, and physical sensation. The air entering your lungs, the oxygen binding to hemoglobin in your blood, and the neuronal firing that processes these thoughts all depend on electromagnetic forces operating across empty space to create the rich, coherent experience of being alive in a solid world. Understanding how emptiness creates solidity transforms rather than eliminates the wonder of physical existence. The solid reality you inhabit becomes more remarkable when you understand it as an emergent masterpiece created by universal forces operating with mathematical precision across vast empty spaces. You live in a cosmos where nothingness organizes itself into everything through principles elegant enough to be described by equations, yet complex enough to create conscious observers who can discover and appreciate their own underlying emptiness. If you found this exploration of reality's deepest structure fascinating, give this video a thumbs up and subscribe for more journeys into the hidden physics that makes existence possible. Check out my video on why time only moves forward the same. Thermodynamic principles we've discussed here determine the arrow of time that governs cosmic evolution. Tonight, when you touch anything at all, you'll experience it with new awareness, not as contact between solid objects, but as electromagnetic communication across empty space, connecting you directly to the fundamental forces that shape the universe itself.